This is one of the driest places on Earth. Sometimes it feels like being on the Moon or Mars.
During the day is a fantastic place, but during the night is absolutely astonishing.
Hi everybody, welcome to this second mission of the Journey Through the Extreme Universe. I'm Alba Fernandez Barral, I'm the Outreach and Education Coordinator of the CTAO Observatory. And today here with me, we have a very special guest, our mission commanders for this second webinar, Roberta Zanin, who is the project scientist of the CTAO Observatory. Roberta is going to delve into the technology of CTA. She's going to explain why CTA needs different types of telescope and how these telescopes catch gamma rays indirectly. But before inviting Roberta to join me here on the screen, let me remind you that if you have any comments, if you have questions, you can already share them with us in the section comments of the CTA Facebook and YouTube channels or during Roberta's talk. At the end of her presentation, we are going to gather some of those questions and we will try to answer them. And with that, let me invite Roberta to join me. Hi, Roberta.
Hi, everybody.
How are you? So before starting with the presentation, let me introduce you to our audience. Roberta is a doctor in astrophysics, specialized in ground-based gamma ray astronomy. As I said, she is the project scientist of the CTAO Observatory. So she has a key role in all the science-related aspects of the construction, the operation of the observatory, and also she works to ensure that the design, the implementation, the science verifications of CTAO achieve actually the science goals of the project. So thanks a lot, Roberta, for joining us today, and whenever you want.
So thank you, Alba, for the nice introduction, and let me thank you all of you for joining this appointment of the journey through the extreme universe. So I have divided this seminar into two parts. So first, I will shortly introduce the very high energy astrophysics with a focus on the technique that CTA, this instrument that we will be talking about, is going to use. This is the imaging Cherenkov technique. The second part, we will focus more on CTA and we will look at how the CTA is designed. So what's the instrument design and what's the reason behind this design, which is of course a scientific reason. So let's start with the introduction. I will be rather fast because Alba has already introduced you in the first appointment of this series. So this is I think in the common view of our sky there is an image like this. So this is you can see here plenty of stars, of galaxies, and you can recognize spiral galaxies or and this is actually an image of the Hubble Space Telescope. So it's an image in the visible wavelengths. And it's plenty of great details because this instrument, this telescope, has provided us with a huge variety of images of our sky in these wavelengths. So this is a spiral galaxies. This is a nebulae. But as I said several times already, this is only in the visible wavelengths. So this is a tiny region of the entire electromagnetic electromagnetic spectrum, sorry, and this is as you see here you can see it goes from radio up to extreme gamma rays, and if we compare these with the with music, for instance, visible light would be just 1 octave of a 15-meter piano. So try for a second to imagine that you are listening to a symphony, and this symphony is played just with 1 octave of the piano. So you will barely be able to recognize the symphony. And the very same concept can be applied to astronomy. So if only when we look at the entire at the sky from the entire electromagnetic spectrum, then you can really recognize the beauty of our universe, and we can study what's behind this beauty in detail. Let's say, no. So here you have an image of the. Let me start. Sorry. This is a supernova remnant. So despite this is a kind of object that we can see in the high energy sky. So despite the kind of object, so here you can see an image of these remnant, which is composite. So you see the image in optical, in radio, in X-rays, that it's very peculiar in each of these wavelengths. But only when we combine all these information and these images in the composite image, we can really appreciate the beauty and how actually it works. So I hope with this to have convinced you that in astronomy is very important to look to study the phenomena of our extreme universe from different perspectives. So looking at them across the entire electromagnetic spectrum, from radio up to the most extreme, the most energetic photons, which are the gamma rays. So here you have the full electromagnetic spectrum, and you can see the different kind of instruments that are used, the different kind of telescopes that are used to actually look at the different wavelengths, at the sky in different wavelengths. So you can recognize the radio parabolas, the classic optical telescope with a dome, and then there are also several satellites, because there are specific wavelengths where our atmosphere is not transparent, so it doesn't allow these wavelengths to reach the Earth. So the only way to study those phenomena in those wavelengths is actually to send a satellite above our atmosphere. And this is true also for gamma rays up to a certain energies. So let's say up to more or less 1 million of electron volt. 1,000 of millions of electron volts. So 1 giga electron volt. But above this energy, satellites cannot see the gamma rays. So the only way we have to detect those photons is actually to go back to the ground and indirectly detect them. So this is what we do with the imaging Cherenkov telescopes. And here we can try to understand how this technique work. So as I said, we are not directly looking at the gamma rays, because what happens when the gamma rays enters the atmosphere, the Earth atmosphere, is that it produces, when it interacts with one of the molecules of our air, it produces a cascade of secondary particles, and these secondary particles then travel towards the ground. And what we can actually detect is not the primary gamma rays, but the secondary particles. And how do we actually detect them? So what happens is that we these particles that travel faster than the light in the medium, in the air, produce the Cherenkov light. So the Cherenkov light is the Cherenkov effect is an effect that produces visible light. So this is light in the optical wavelengths that is collected by these large reflective surface, which are basis, one of the bases of the main point of the Imaging Atmospheric Charcoal Telescope. And then they are focalized, so this reflective surface focalize this light, this visible light, into a pixelized camera. And here you can see what you would, how this cascade of secondary particles would look like in our camera. So you see a kind of ellipse, and now we will see in a second which kind of information we can gather from this image. But the main point so here is that we are looking at gamma rays indirectly through the detection of the Cherenkov light that is produced by secondary particles, and all these is something super fast. So this is a 10 nanosecond snapshot that would not be that our eyes could not even appreciate. So in this way, with a fast electronics, we can record those super fast flashes and look at them as events in our pixelized cameras. And this is what you see in our camera. So this is another view of this of one of the gamma rays. So you can see here that it kind of resembles an ellipse. And actually, the way we this Illas, this is a famous astronomer that 2 decades ago, 2-3 decades ago, invented a parameterization for these images. So that now we call them Illas parameter. So what we do is we approximate this image to an ellipse, and the major axis of the ellipse provides us the information of the direction of the primary gamma ray. And the amount of charge that we detect is included in these approximate ellipses is giving us the information of the energy of the primary gamma rays. So by basically studying these parameters, this parameterization of the image, we can reconstruct the primary characteristics of the gamma rays. Unfortunately, gamma rays are not the only particles that reach the atmospheres. There are plenty of what we call the cosmic rays, of charged particles that reaches the atmosphere as the gamma rays produce cascade of secondary particles. And these cascades of secondary particles that are not produced by a gamma rays, but by a random cosmic rays, are detected as well by these kind of telescopes. So one of the main difficulties of this technique is actually to disentangle the gamma rays that we want to detect and are coming directly from the source that we are pointing at, from the images of those cascades that are produced by a random cosmic ray. And the way, so here you have an image, for instance, of a proton produced by a cascade, by a cascade produced by a proton. And you see that it looks differently. So basically, it has a smaller eccentricity, and just without going into the details, so studying the differences in these parameters of the images, we can actually compute a probability that this event is produced by a proton, a cosmic ray in general, or a gamma ray. And this is really, in few words, how the imaging Cherenkov technique works. As you saw in the picture, all the picture that I'm showing here, you can see at least two telescopes. So why so? Because by looking at the same cascade, at the same event with two or more different telescopes, you can improve significantly the precision of the direction of the primary gamma rays. So we can really measure with much more precisely the direction of the primary gamma rays. So in scientific terms, it means that by looking with two or more telescopes, so in stereoscopic, this improves the angular resolution. So that's why from the second generation of IACTs, of Imaging Cherenkov telescope on, we have always been building stereoscopic systems, so arrays of telescopes. And as I was saying, so this technique, this field of the very high energy astrophysics started with this technique, the imaging atmospheric Cherenkov technique, and is fairly recent. So the first telescope that detected the first signal from the Crab Nebula in 1889 was the Whipple telescope in Arizona, and this was a standalone telescope. After that, there was a second generation of stereoscopic telescopes, IGRA in the Canary Island of La Palma, Kangaroo in Australia, and these were built in the 19s. And now there is the third generation of ICTs that is currently in operation, and we have three main facilities. One is HES in Namibia. Then we have MAGIC with two telescopes in the Canary Island of La Palma, the same site of IGRA, and Veritas, which is in Arizona, basically close to the same site of the Whipple telescope. So with the first and second generation of telescope, they have been proven that this technique, the imaging Cherenkov technique, is actually working, and was detected less than 10 sources. So by the end of the 90s, the very high energy sky was looking had less than 10 sources. Now with the advent of the third generation, so these currently working facilities, now we have discovered more than 200 sources. So it's clear that a giant step forward was done in the last decades with this technique that has not only been proved successful, but has also reached the point where we can start really producing precision measurements. Of course, this is true with these currently running facilities, true only for the very bright sources. So we can really detect and produce precision measurements only for those sources which are very bright, for which the statistics is high enough. But it's certainly true that with this technology, by improving the capabilities of this telescope, we can have a much deeper insight on the very high energy sky. So there is still a large discovery space, and this is particularly true in this moment where you have heard for sure that we have entered the era of the multi-wavelengths, but also the multi-messenger astronomy. So we are not trying only to combine information from different wavelengths, as I was pointing at the beginning, but also from different messengers. So photons with neutrinos, or charged particles like cosmic rays or gravitational waves. So in this moment, it's very, very important to try to build a new instrument which has an improved capabilities with respect to the currently running facilities, and by using the very same technique that I was describing, this imaging Cherenkov technique, we can now build an observatory, something that will serve the entire community and will be able to provide to any scientist in the world the data of the source he or she wants to study. So this is really a new step, a new starting point for the very high energy astronomy, because we moved from from a reality of experiments where so far we have discovered the sources and we have counted them, and just in the last years, in the last decade, we have started really producing precision measurements of the brightest gamma ray sources to have a wider role in the astronomy, in the multi-wavelength and multi-Wessager astronomy as an observatory. And for this reason, we are now in the process of building the next CTAO observatory, so the Cherenkov Telescope Array Observatory. And this will be geographically distributed. So this has a legal entity, which is ad interim CTAO GmbH, but is in the process of becoming an ERIC, where ERIC means European Research Infrastructure Consortium. This observatory is geographically distributed, so has the headquarters that are currently in Bologna and in Heidelberg, but will be soon only in Bologna. Has a site data management center in Zeuthen, close to Berlin, and has two array sites. One which is looking at the northern sky in the Canary Island of La Palma, and one is looking at the southern sky in Chile at Paranal. So now now that we have understood that why we need a new a next generation of very high energy gamma ray instrument, gamma ray detector, which is going to be CTAO, and we have understood which kind of technologies these observatory will have. This new instrument that will run as an observatory will have. This is the imaging atmospheric Cherenkov technique. We try to understand what's the design of the instrument. So it's based on IACT, Imaging Cherenkov Telescopes, and this has to provide a giant leap with respect to the currently running facilities in terms of scientific performance. So what we call sensitivity, energy resolution, angular resolution, but also in the energy coverage. So when we talk about very high energy gamma rays, we talk about gamma rays above, let's say, tens of GeV up to hundreds of TeV. And the currently running facilities explore the range between 50, 80 GeV up to tens of TeV. So with CTAO, we plan to increase the energy window and to move to much higher energies, knowing that these the most extreme energy windows, so up to 100 of TeV, has been poorly explored so far. So there is a huge discovery space there. But we also plan to go a little bit lower in energy, down to 20 GeV. And we will understand in a second why moving from 80 GeV down to 20 TeV is very critical and very important from a scientific point of view. So these are the basic characteristics that are behind the design of the Cherenkov telescope array. And now, to understand the design, I want to stop for 1 second on the science case of CTAO. And let me just define three energy ranges and split the science cases in three categories, one for each energy range. So we have what I call here the sub-TeV, so between 20 GeV and hundreds of GeV. Then we have the TeV between hundreds of GeV and tens of TeV. And then the multi-TeV, which is above tens of TeV. So each of these energy range has its own driving science cases. Here I listed them. I don't plan to go into any detail of this science case because you will hear about them in the coming seminars. But the main point is that for the sub-TeV energy range, the driving science case are those connected to transient sources, to cosmological sources, whereas for the TeV we are dominated by those by precision studies, surveys, dark matter searches, and at multi-TV, the driving science case is the one related to the pevatons, which are astrophysics sources capable, which are able to accelerate particles, charged particles, up to the most extreme energies in our galaxies, which is about 1 PeV, so 10 to 15 electron volts. And for each of these energy ranges, so we have one specific telescope design. So the telescope has been optimized for the science cases which are listed here in each of these energy ranges. So we have the large size telescopes, the LSTs, for the sub-TV energy range, the MSTs, the medium-sized telescope for the TV energy range, and the small-sized telescope, SST, for the which are optimized for the multi-TV energy range. So let's now try to understand why there is this link and how this link works between the science cases and the telescope design. So I said that for the sub-TV energy range, which is the one between 20 GeV and hundreds of GeV, this is dominated by transient and cosmological sources. So here in this plot, without going into any detail, the takeaway message is that the most extreme sources, which are the ones at cosmological distance, are also the ones at cosmological distance, so closer, let's say, to the origin of our universe. And as such, they are also, since they are extreme phenomena, they also last for a short period, for a short time window. So there is a strict correlation between the flux variability, the time scale of the flux variability, which can be second, minutes, hour, and the distance of the source. So now just to mention one, the gamma ray bursts, which are among the most extreme phenomena in our universe, which are also the farthest away, are the one which shows a flux that can last for few seconds. So a burst that can last for few seconds up to 2 minutes. So there is a link between transient and cosmological sources. When transient means these are phenomena that produce an emission for a very short amount of time. There is another problem because we're looking at cosmological sources. So it means that these sources are very far away, and the photons that are produced there need to travel a long way before reaching the Earth. And during their travel to the Earth, they are absorbed by the lower energy photons of the extragalactic background light. So the extragalactic background light is accumulated radiation due to the star formation along the history of the universe. These are low energy photons, and they, by interacting with the very high energy gamma rays, they absorb them. So basically, these gamma rays are not able to reach the Earth. Fortunately, this absorption is energy dependent. So this means that the absorption affects the highest energies in higher energies in the close by universe, and then it affects the lower energies if we go farther away. So this means that if we want, if we observe at 1 TeV, if we can measure what we call the nearby universe, which means up to 100 megaparsec from us. If we go down to 100 GeV instead of 1 TeV, so if we go down 1 decay in energy, then we can explore a universe, a volume of the universe, which is 10 times larger. And only if we reach the 20 GeV, then we have access to the universe down to its origins. So now you can understand why it's very important to go down to 20 GeV. And this, the fact that CTAs can reach these, what we call this the energy threshold, this 20 GeV, is fundamental from a scientific point of view, because it allows us to explore a much wider region of the universe. So now, as I said at the beginning, cosmological sources that we understand are also transient sources and are visible only if we can look at the lowest energies, where lowest means 20, 30 GeV. These are detectable by the mainly by the large size telescopes. So these are the IACTs with the largest reflective surface. So why so? Why do we need a large reflective surface to go down in the energy threshold, so to go down to 20 GeV? Because these are the lowest energy photons, gamma rays, that produce smaller cascades and then a smaller amount of Cherenkov light. So we need large reflective surface, large mirrors to actually be able to collect all this light. On the other hand, we know that the spectrum of the particle, so the emission of these, the radiation that the astrophysical sources produce, is, if we look in our energy range, which is this the shadow region here, they resemble a kind of power law. So they basically decrease significantly by increasing the energy. So this means that at low energies, we have plenty of, low energy means tens of GeV for us, we have plenty of gamma rays. But then if we move towards the multi-TeV and multi-TeV energy ranges, then the amount of photons is much smaller. So this means that we need to have a large collection area to be able to detect a significant amount of these photons. But these are energetic photons, so this means that they produce wider and big images in our cameras, and for which to detect these images, we don't need a large reflective surface. So this allows us to build smaller telescopes, but in this case, we need many of them to be able to collect the correct amount of primary gamma rays. So this is why we have few large size telescope in the middle of the array, and then we have a circle around this large size telescope of medium sized telescopes, and then an outer ring of small size telescopes to cover a large area, which is, in the case of CTAs, about 4 square kilometers. So let me just say a few words about the characteristics of these telescope designs. So we have seen the large size telescopes, which have a 23-meter diameter. They weigh more than 100 tons, and they are as high as a 15-floor building. The medium-sized telescope has a 12-meter diameter. It's a weight of 82 tons, and it is as high as a 7-floor building. Whereas the small-sized telescope is less than 20 tons and is much smaller, as high as a 3-floor building. Here you have, I let you with the, these are what we call the layout. So how we place the telescope on the ground at the two sites. So you can see here in the southern hemisphere, the southern site, which has, for the full scope configuration, has 100 telescopes. And the northern side, which is smaller and includes only LSTs and MSTs, and it is smaller because the area available is much smaller. So here we are on the top of a mountain where the available area is rather limited, and the full array is covering an area of about half a square kilometer. So this is all what I have for you today, and so let me just conclude shortly. Basically, the CTAO observatory that will start construction soon, as soon as the ERIC, this legal entity, will be in place, will inaugurate a new area of the astrophysics. Thanks to the synergy of the three complementary telescope designs. It has certainly a rich scientific program that will address still many open questions, but it has also a huge discovery power. I'm sure that in the next seminars, webinars, you will be looking in details at the scientific program of this future observatory. And let me mention that this will be the first ground-based gamma ray observatory that will provide scientific data to the entire scientific community. And thank you for your attention.
Thanks a lot, Roberta, for this super interesting and detailed presentation. I really enjoy it. We have already some comments, some questions in our Facebook and YouTube channel, but let me remind everybody that we are going to start now the question and answer session. So this is the moment. If you have a question, do it now. Let's start with a question by Rupert in Facebook. He is asking if the projection or rotation of the ELAS parameter is the only information that we have for to analyze, to parameterize the events. And he also says if the position of the detector, how does that relate to the baseline distances?
So about the projection orientation of the ELAS, no, it's not the only information. I mean, this is the basic information, but there are plenty of them that we use actually to discriminate between the kind of event that we are looking at. As I was telling you, there are what we call the electromagnetic showers, so the showers produced by primary gamma rays that we want to detect, and there are showers produced by cosmic rays. So in order to discriminate between these two kinds of events, then there are several parameters that we use. Many of them are related to the ellipse. So like the third, the fourth momentum of the ellipse, the wide and the length, but there are also more complex ones. So it's not the only information; it's just the basic one. And the second question is about the position on the detector, the field of view. How does that relate to the baseline distances? So the baseline distances, you mean the telescope spacing, I guess. So the telescope spacing, I have, let me go back to one slide. So I have here, so I have here a sketch of of how we can place an array of telescope and what's the usual telescope distance. So the telescope distance is a very critical parameter that we need to study when defining the array layout, because we want to have, as I hope to have conveyed the message, that we want to have the largest possible footprint to increase the statistics at higher energies, but at the same time we cannot place them. We cannot place the telescope too much farther away, because otherwise the telescope would not see at the same shower. So thinking that the Cherenkov light pool has a diameter of 120 meter, this gives you basically the average spacing between the telescopes. Then the spacing is also related to the field of view of the camera, but this is a next next step, let's say the spacing. Okay, but let's in first approximation we can say that this mainly depends on these things that I have described.
Thanks a lot. We have another question by Garima about actually the events. It's a common question. Why does the Cherenkov signal seem as an ellipse?
I don't have okay, so let's I have a picture, but I don't have it in the slides where it's easy to see why it translates to an ellipse. But in few words, we can say that the width of the ellipse, so the minor axis of an ellipse, gives you the transversal, the longitudinal, the transversal development of the shower. So this development of the shower translates into the minor axis of the ellipse, whereas the longitude development of the showers is translates into the this major axis of the ellipse.
Perfect. It's kind of the projection, not like
yes,
cut of the cone of the. Okay, and we have another one by Rupert here, actually related to one of the latest news in the field. Are there energy overlap for TV for CTA and LASO? Possibly
yes,
science cases for simultaneous observations?
So there are the overlap is there. I mean, LASO is looking about tens of TV, and up to much higher energy than CTA. So it has produced results up to 1 PV, actually almost to 1 PV. So there is an overlap between tens of TV up to hundreds of TV. So there is the possibility for simultaneous observation mainly for the northern array of CTA, because LASO is located in China, so it's looking at the northern sky. And what is relevant is that LASO is so it's using a different kind of technique, but and has a much larger collection area, so that's why it can reach higher energies, but has a much poorer angular and energy resolution. So these two kind of technique are kind of complementary. One is more sensitive, and the other one is more precise. So even in the overlapping energy range, there is a large room for complementary, and really this will provide a wider exploitation of the scientific results.
Okay, so let's stop here. Thanks a lot again, Roberta, for the nice
Thank you
talk,
to you.
for the nice answers. And especially thanks to the audience that joined us today in this second webinar. Just a reminder, don't forget to follow us on Facebook, on Twitter, on Instagram, and also subscribe to our YouTube channel in order to stay tuned for the next webinars. As Roberta already mentioned, we are going to start with the science cases of CTA. Next month, in June, we are going to start with the cosmic rays, these extreme particle accelerations that actually Roberta mentioned today. And that's it. Thanks a lot to everybody, and see you in the next event. Ciao, ciao.